Hey, this is Miss D, and this is the Circular Motion and Forces Test Review. This is Unit 3. So the first two questions that you have here are using the formula where you're going to be calculating universal gravitation. So we're solving for the force of gravity, and you're using big G, which is 6.67 times 10 to the minus 11th, and you're going to multiply by mass 1, mass 2, and then divide by the total distance. So what's the gravitational force of one 30 kilogram object and one 70 kilogram object that are 10 meters apart? So we're just going to go ahead and plug in. Force of gravity equals 6.67 times 10 to the negative 11th. Coach Hawes is being a jerk.
Oh no, this is good.
Times 30 times 70 divided by 10. Coach Hawes just blew me up on his iPad. That's why I'm laughing. Okay, so you're going to type that into the calculator, and the easiest way to do this on the calculator, you guys, is for you to actually take and put everything that we just wrote down, but take another parentheses and put it on the outside here, and another parentheses and put it on the outside here, and then you're going to type all that in. So I'm going to go ahead and I'm going to say it out loud, and if you actually have a calculator and you follow along, you should get the same answer. You're going to go parentheses, parentheses, 6.67, and then on the calculators at school you have to do the second EE to do your exponent, to the minus 11th, parentheses. Then it's going to be open parentheses, 30, close parentheses, open parentheses, 70, close parentheses, and then another close parentheses. Divide that by parentheses 10 squared, close parentheses, and you get 1.4 times 10 to the minus 9th. And that is my force, so that's going to be in newtons. Number 2, it says, what is the force of gravity pulling the Earth and Moon together if their distance is 3.8 times 10 to the 8th, and the mass of the Earth is that, and the mass of the Moon is that? So I'm going to go ahead and write that all up here. And so you're going to have 6.67 times 10 to the minus 11th. Remember, we want that in parentheses. We want an extra parentheses here. We're going to multiply times the mass of the Earth, which is going to be 6 times 10 to the 24th. And the mass of the Moon, 7.35 times 10 to the 22nd. You guys can't see that. Let me rewrite it. 6.67 times 10 to the negative 11th. 6 times 10 to the 24th. 7.35 times 10 to the 22nd. Parentheses all the way around that, divided by the distance between them, 3.8 times 10 to the 8th. Thank you, Eric. And we're going to square that. So, typing it into the calculator, parentheses, parentheses, 6.67 second EE minus 11th, parentheses, times 6 second EE 24th, parentheses, 7.35 second EE 22nd, close parentheses, divided by 3.8 second EE 8th to the second power in parentheses. Don't forget to put that in parentheses, otherwise you'll get the wrong answer. Equals 2.037 times 10 to the 20th. So basically 2 times 10 to the 20th, and that's the force in newtons. It's a multiple choice test. Relax, you guys. All right, next question. Number 3. The orbit of B is 3 times farther away than the orbit of A. So I'm going to say that the distance between A and the center is x. And then the distance between the center and B is 3 times that, which would be 3x. So how does the gravitational force of A to x compare to the gravitational force of B to x? So our formula is force equals gravity, mass 1, mass 2, divided by distance squared, right? So the only thing they're giving us here is information about the distance. So assume that we have all this, right? And so we're just going to have gravity, mass 1, mass 2, divided by x squared. Or we could have gravity mass 1, mass 2 divided by 3x squared. That's going to give you 9x. That'd be over 9x. So what you can see is that this, the gravitational force of A to x, is going to be much, much stronger, much more force than B to x. So A to x is 9 times more. Or you could say B to x is 9 times less. And that's pretty complicated, but you got to remember when we talked about it on the board the other day when we looked at distance and we looked at the factor of force, it did that. So it's an exponential inverse relationship. So the farther away B is, then like the much more less the force is, right? So that is 3. Number 4, it says imagine a ball twirling on a string. So we've got the arrows. If the string breaks in the location below, draw an arrow on the ball showing which direction the ball would go. I don't actually know what location they're showing the string breaking, so we're just going to actually break the string. I think that they're showing the string breaking here. So if the string breaks there, the ball is going in this direction, right? So the ball would keep going. Let me see if I can draw a straight line. The ball would keep going in a straight line like that because of inertia. And that's it. Bye, Eric.
Bye.
All right, number 5. A ball is revolving around the dot in the center. So it's going in a circle all the way around, kind of like the Earth goes around the sun. Let me erase that. All right, so it says draw the direction of the centripetal acceleration on the diagram and label it the force, the centripetal force. Okay, so the deal is this. The acceleration is in towards the center because it's constantly being pulled in towards the center. That is the definition of a centripetal force. It's that pull in towards the center. It's why if you're holding a little kid and you're swinging them around by their arms are like being pulled out of their socket because you're pulling them in towards the center. So you would label this the centripetal force. You could also label it acceleration because they're the same thing, because the centripetal force is what's causing the acceleration in towards the center, because, you know, force causes acceleration. That's that. Assuming the ball and the dot have a mass, how would the gravitational force change between them if you move the ball in? So let's say I move the ball to like here, okay? So is it going to be more or less gravity if it's closer? And the answer is it's going to be more gravity, more force, because it's closer. How about if you move it twice as far away? So if I move it here, and let's say that this was x, and now this is 2x, we just did this, it's going to be, it'd be 4 times less, because 2 squared equals 4, right? So that's that. Number 7, where it says we're using F equals ma, so it says a force of 45 newtons is pulling on a 9.4 kilogram box, that's my mass, by a rope across the surface. What is the acceleration? So we use F equals ma. We have 45 equals 9.4 times the acceleration, and we're going to divide both sides by 9.4 to find A. So that is 45 divided by 9.4 equals 4.787, which, you know, to 2 sig figs is 4.8 meters per second squared. All right, a 4 kilogram object and a 12 kilogram object have masses that are 8.7 meters apart. And this is not using F equals ma, so that is a typo, because this is going to use the same formula that we've been using, which is the force of gravity equals gravity times mass 1, mass 2 divided by the distance squared. So that is going to be 6.67 times 10 to the minus 11th times 4 times 12, put that in the double parentheses, right? And then divide that by 8.7 squared And type that into the calculator, 6.67 second EE minus 11 times, hang on, I forgot a parentheses, 6.67 second EE minus 11, close parentheses, times 4 times 12, close parentheses, divided by 8.7 squared equals 4.2 times 10 to the minus 11. 4.23 times 10 to the minus 11th, which is a really, really little number. But you're talking about something that weighs like 4,000 paper clips and something that weighs 12,000 paper clips. So if you had like, I don't know, a bag of flour and like 2 bags or 3 bags of flour sitting 9 meters apart, how much gravity do they exert on each other? And that's like saying, I don't know, if your dog's in the backyard and your cat's sitting on the windowsill in the house and they're 30 feet apart, how much gravity do they exert on each other? And the answer is not very much. So next question. How would your weight change if you increase the mass of the Earth? It would increase because you multiply times the gravitational force, and that's based on the mass of the Earth. How would your weight change if you decrease the radius of the Earth? So that would be, we're going to decrease this. So we're going to divide by a smaller number. So if I divide 2 by 2, I get 1, right? 2 divided by 2 equals 1. What if I divided 2 by 1? I would get 2. So if you divide by a smaller number, you end up with a bigger answer. So it would also increase. So if you decrease the radius of the Earth, you're going to increase the force, I think. That makes sense, right?